Hello, AP Chemistry students. We're now at part 2 of Unit 4, and this one's going to focus on the types of reactions. And these are associated with sections 4.7 through 4.9. We skipped section 4.6 at the moment because that's all about titrations, and the three major types of chemical reaction that we're going to talk about today have titrations associated with them. So I figured it'd be better to go over the reactions first. So our learning objectives for this one are to identify a reaction as acid-base, oxidation reduction, or precipitation, to identify species as Bronsted-Lowry acids, bases, and or conjugate acid-base pairs based on the proton transfer involving those species, and then to represent a balanced redox reaction using half reactions. So we're going to be focusing on acid-base reactions, redox reactions, and precipitation reactions. These are three of the most unique types of chemical reaction. A lot of the types you might think about, like rusting or combustion or neutralization, all of those can be classified as one of these three. So these are the three broadest type of chemical reactions. So an acid-base reaction is a transfer of one or more protons, which is a way of referring to hydrogen ions, since hydrogen only has a proton and an electron, and if it loses an electron to become a cation, it's only a bare proton left. So transfer of one or more protons from one chemical species to another. Redox reactions are a transfer of one or more electrons from one species to another. Redox are by far the most common type of chemical reaction. And then a precipitation reaction, which is the formation of an insoluble or sparingly soluble ionic compound resulting from the mixture of soluble ionic compounds. So first we're going to talk about acid-base reactions. And from a little historical context, one of the first sort of classifications of acid bases, one of the first definitions of acids and bases were developed by this dude, Svante Arrhenius. He defined an acid as an ionic substance that dissociates in water to produce hydrogen ions, also called protons. So something like HCl, hydrochloric acid, is an acid because as an ionic compound, it splits up into hydrogen ions and chloride ions. And the hydrogen ions in the solution are what make the solution acidic. He also defined a base as an ionic substance that dissociates in water to produce hydroxide ions. So kind of a similar concept. We have an ionic substance, and this one has hydroxide as an anion. So when it splits up, it makes Na plus and OH minus. So basically, a solution that has hydrogen ions is considered to be acidic, and a solution that has hydroxide ions is considered to be basic. So some common Arrhenius acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid. Usually a ionic substance that has hydrogen as the cation. And then common Arrhenius bases: sodium hydroxide, ammonium hydroxide, potassium hydroxide, lithium hydroxide, ionic compounds that have hydroxide as the anion. After a lot of experiments were done and some history passed, we got another definition of acids and bases, which we call the Bronsted-Lowry acid-base definition. And this one is a little bit more accurate and more common in terms of looking at acidic and basic solutions and the reactions that occur between them. And in this definition, a Bronsted-Lowry acid is a substance that is capable of donating a proton, aka a hydrogen ion. So sort of the same idea as a Arrhenius acid, but where this definition differs is when we consider bases. So a Bronsted-Lowry base is a substance that accepts a hydrogen ion. So instead of giving up hydroxide, now we're defining bases as something that takes those H pluses and then incorporates them into the molecule. It absorbs those protons, those hydrogen ions. So a good example of this is the dissociation of acetic acid / vinegar. In this reaction, we have CH3COOH. So this is a acetic acid molecule, and it's written kind of backwards. But here's the hydrogen ion that it's going to lose. And it's going to lose it, and it's going to separate into the solution. So it's going to make H plus ions. And then in this case, the water molecule is actually going to act as a base and accept that hydrogen ion. It's going to incorporate that hydrogen ion into the molecule. And what we end up with is acetate, which is acetic acid without its proton, without its hydrogen ion. So you can see now it lost that H, and now it has a negative charge because it lost a positive charge. And now the water becomes H3O plus. So the water gained the H plus ion into itself and gained a third hydrogen and then gained a positive charge as a result because it started neutral. And you also notice that in this equation, we have the double arrow here. This usually refers to something that has an equilibrium, something that's reversible. We're going to talk a lot more about that in a later unit, so don't worry too much about that, but just know that this reaction can go back and forth in both ways. And if we consider that it's reversible, our acetic acid is going from acetic acid to acetate, so it's giving up its hydrogen ion. So this is our Bronsted-Lowry acid. The water molecule is going from H2O and then gaining the hydrogen ion, which means that it's a Bronsted-Lowry base. And if we consider that the reaction is reversible, we can look at it backwards and see that in this case, the acetate is going to be the base because it's going to gain the hydrogen, become acetic acid. And in this case, the H3O plus is going to lose its proton to become the base in the first one. So when we consider reversible reactions, the thing that was the acid sort of becomes a base, and the thing that was the base sort of becomes an acid if the reaction was to be reversed. And sometimes we're going to end up talking about acids and bases as being strong or weak. And strength is not correlated to the concentration. It's not like how many H plus ions there are in the solution, how much acid there is in general. Strength more has to do with dissociation. How likely a acid is to lose its proton, or how likely a base is going to accept one. And like I said, once we talk about equilibrium, we're going to go into a lot more detail on that. So don't worry too much about it now. As you can see in the diagram below, the strong acid on the left, all of the ions have split up. So all of the little red hydrogen ions here are off on their own. Whereas here in a weak base, some of the hydrogen ions are still attached to their cations, so they haven't been released yet. So something that is more willingly able to dissociate is considered to be strong, and something less willing to dissociate is considered to be weak. All right. So a couple slides ago, I talked about the H3O plus, that thing that water molecule becomes. This is called a hydronium ion, and it's not so much that this actually exists in solution, but it's a way to represent hydrogen cations dissolving in water and to show their equilibrium. So H3O plus is in equilibrium with H2O and H plus. So we consider this to be a reversible reaction. So you're going to see H3O plus a lot in the acid-base chemical equations. And the main reason to do that is to show how water is involved in the process, how water sort of acts as a base to pull hydrogen ions off of acids in the first place. So it's really important in the balancing of things. Since since water molecules can both lose and donate hydrogen, depending on like which way that we're looking at the reaction, water is something unique that is both an acid and a base simultaneously, depending on the context, depending on what it's reacting with. And molecules that behave this way are referred to as amphoteric. So something that's amphoteric is something that can both behave as an acid or behave as a base. So in this case, we show water behaving as an acid where it's losing one of its hydrogens to become H plus and OH minus, or we can look at water being a base and gaining a hydrogen ion and becoming H3O plus. Water isn't the only thing that's technically amphoteric. Things that can both gain or lose electrons, like this HSO4 minus, this can give up its H and become SO4 2 sulfate plus hydronium, or it can gain a hydrogen from a water molecule. It can pull it off and become sulfuric acid and a hydroxide. However, something like this is going to be more controlled by equilibrium, and its likelihood of acting as an acid and its likelihood of acting as a base are not going to be the same. The thing that's especially unique about water is that water's ability to act as an acid and water's ability to act as a base are sort of equally likely. It's both 50% acid and 50% base in a sense. So I talked a little bit about this earlier in terms of acids becoming bases after they react, and bases becoming acids after they react. The way we refer to this is as conjugate acid-base pairs. So in that example before, we had the acetic acid, and it gave up its hydrogen ion and became acetate. It became CH3COO minus without that extra hydrogen. And we call this a conjugate acid-base pair because it starts as an acid. It gives up its hydrogen ion, and then it becomes a base, which can then gain a hydrogen as if it's going in the backwards direction. And the water molecule here, the H2O, which was taking that hydrogen ion, which was accepting it, like a Bronsted-Lowry base, that's going to have a corresponding acid on the other side when we have H3O plus that is likely to give up its hydrogen ion to acetate to do the backwards reaction. So conjugate acid base pairs are basically the acid that becomes a base, that becomes a pair, and then the base that becomes an acid is also a pair. And the strength of one is going to sort of correlate to the strength of the other in sort of an inverse relationship. So something that starts as a weak acid is going to become a strong base because this didn't really want to give up its hydrogen. So it's likely that it's going to want to gain that hydrogen back. All right, let's do a practice. So let's considering that ammonia acts as a weak Bronsted-Lowry base, let's predict what the products of this reaction are going to be based off of the mechanics of how Bronsted-Lowry acids and bases work. So we know that since ammonia, NH3, is a Bronsted-Lowry base, it's going to be something that gains hydrogen ions, that gains protons. And in that case, that means that the water is going to act as the acid. So the water is going to give up one of its hydrogens. So we know that when water gives up a hydrogen, it becomes H plus and OH minus. And since the ammonia in this case is going to be gaining a hydrogen ion, we're going to add that hydrogen ion to the NH3 molecule. So what that's going to end up looking like is this. The NH3 plus the H2O is going to form NH4 plus and OH minus. So as we recall from those slides we just looked at, the water molecule is going to split up into H plus and OH minus. So we have the OH minus over here, and then that H plus then attached to the NH3 and became NH4 plus. So it gained a hydrogen, and it also gained the positive charge of the hydrogen ion since the ammonia started as a neutral compound. So the ammonia in this case was the Bronsted-Lowry base. The acid was the Bronsted-Lowry acid. And then the NH4 plus is the conjugate acid. So this becomes a conjugate acid base pair. So it starts as a base and then becomes an acid. And then the water becomes the OH minus. So that's also a conjugate acid base pair. And it becomes a base as a result. So H2O is the acid and then OH minus is its conjugate base. Since NH3 and H2O are a weak base and an acid, we can assume that NH4 plus and OH minus are going to be stronger. Though not all bases give up OH minus, but all strong bases do, as we saw in those early examples of like sodium hydroxide, potassium hydroxide, etc. But weak bases can create hydroxide in solution, therefore making the solution itself basic by stealing protons from H2O, like we saw here. So even though there's no hydroxide associated with the ammonia, it created hydroxide in solution by stealing protons, hydrogen ions, from the water molecules. All right, now let's talk about redox reactions. So this is going to be a bit different. We're gonna look at some more chemical reactions, but the mechanics here are going to be slightly different because instead of trading hydrogen ions, we're going to be trading electrons. So the main idea here, redox reactions are, like I said earlier, one of the most common types of chemical reactions, and they consist of two parts. There's the process of oxidation, which is when an atom or molecule loses electrons, and there's the process of reduction when an atom or molecule gains electrons. And there's a mnemonic device that a lot of people use that is oil rig to sort of help remember which one is which. And this is an acronym that stands for oxidation is loss, reduction is gain. So the reason they're called redox reaction, it's sort of a combination of these two words, is because that one of these can't exist without the other. Both of these processes occur in tandem with each other. Because when something's oxidized, when it loses electrons, those electrons have to go somewhere. So that means something else is going to gain those electrons. So oxidation is sort of the start of the process, and then reduction is sort of the end of the process. One atom or molecule loses electrons so that another one can gain them. And some common examples of redox reactions are like the rusting of metal, like iron becoming iron oxide, energy production in batteries, and even combustion. It's weird to imagine, but burning is all about transferring electrons between molecules. So to sort of analyze how this works, we have a tool called the oxidation state or the oxidation number. And this is an abstract value that we can assign to an element in a chemical equation to help determine the relative numbers of electrons that are gained or lost during a redox reaction. And there are some rules that we sort of follow to determine this. So any element that's bonded to itself is always going to have an oxidation state of 0. So any diatomic molecules, O2, H2, N2, Cl2, Br2, I2, F2, etc., pure diatomic molecules are always going to have an oxidation state of 0. And then also metals like copper, zinc, iron, as long as they're in their pure metallic state, they're going to have an oxidation state of 0 because they're bonded to themselves. There's not going to be any electron asymmetry. Everything is balanced. Everything has the right number of electrons. So the oxidation states or numbers of atoms in a neutral molecule or compound must always add up to 0. So this is like when we're making ionic compounds and we're trying to figure out what ratio the cations and the anions combine in. We always make them so that they're balanced, that the charges cancel each other out. So by that same logic, an ionic compound, any sort of compound that contains multiple types of element, the overall oxidation state is always going to be 0 unless it's charged. Unless it's a polyatomic ion, that means that the oxidation states need to add up to the charge of the ion. So if something has a -1 charge overall, the oxidation states of the elements that make up that compound need to add up to -1. So there are some rules for certain elements. Hydrogen cations are always +1. Alkaline metals are always +1. Alkaline earth metals are always +2. Halogens are always -1, and oxygens are always -2. So these kind of correlate to what you'd predict for their ionic charges. However, oxygen does have an exception of peroxide oxygens, which have a -1 oxidation state, and that diatomic oxygen, O2, has an oxidation state of 0. So these are the predictable rules. These are the rules that we know for sure. However, hydrogen and alkali metals, alkaline earth metals, halogens, oxygens, these are really, really common elements to find. So we can sort of use them as a bridge to figure out what the oxidation states of the other elements that are going to be combined in compounds with them, based off of those rules we talked about earlier, where we know that the oxidation states need to either add up to the charge or add up to 0 if it's neutral. Also, some transition metals are going to have different oxidation states, but some of them are kind of always the same. Silver is always +1, and zinc is always +2. So you don't necessarily need to memorize this. Just know that at least these things, at least be able to predict that these specific elements are going to have oxidation states that are equal to the ionic charges that you would expect for those substances. So let's do a little bit of practice here in determining oxidation states. Like I said earlier, you can use the elements that you know the rules for to predict the oxidation states of the other substances. So for example, if I have CH4, methane, this is not something we usually associate as being an ionic compound. Like we don't usually think about carbon as having an ionic charge, but we can assign it a sort of pseudo charge. We can assign it an oxidation number so that if we do a reaction with methane, we can see how its oxidation number changes, and we can use that to correlate how many electrons it gained or lost. So the way we do this, we know it's CH4, and we don't know what the oxidation state of carbon is going to be because it can be variable, but we do know that hydrogen, unless it's diatomic hydrogen, is always going to be +1. So that means that I have +1 times 4, and if this whole thing is going to add up to a neutral charge, because methane is not charged, we know that the carbon in this case has to be -4, because the -4 has to cancel out the +4 to overall have 0 charge. Next, let's look at ammonia, NH4. We know that it has a positive charge. It's a polyatomic ion, which means that the oxidation states of the elements in ammonia need to add up to +1 overall. So similar strategy as before, we know that hydrogen is always +1. So we have +1 times 4, so we have a total of 4+, and we know that we need to have 1+ left over. So that means that nitrogen in this case is going to have to be 3-. So 3- plus 4+ gives us +1 overall. All right, let's look at this one. Cobalt oxide, CO2O3. In this case, we're going to assume that oxygen is not peroxide. Usually, if something's a peroxide, it'll tell you. And in that case, you know that oxygen is -1. But since it's normal oxygen in a compound, we can know it's a 2- charge. And since we know that there are 3 of them, we have 2- times 3. So that's a total of 6- from the oxygen part of the compound. And then we can use that to determine the oxidation state of cobalt in this case. Since we have a total of 6- and we have 2 cobalts, that must mean that each of the cobalts have an oxidation state of 3+. So that we have 3+ plus 3+ making 6+ in order to neutralize the 6- from the oxygen. All right, let's do some more practice. So what is the oxidation state of the elements in carbonate? This is formaldehyde, and then this is titanium for hydroxide. I recommend that you pause the video and try this on your own. Okay, let's look at the answers here. So carbonate, we know it has to be a 2- overall. It has oxygen, so that's 2-. 2- times 3 is going to be 6-, and it needs to be 2- overall. So 6- plus 4+ is going to get us to 2-. So in this case, the carbon has an oxidation state of 4+. All right, this one, we have a carbon, a hydrogen, and an oxygen. The hydrogen is always going to be 1+, so 1+ times 2, that's 2+. We know oxygen is always 2-, so then 2+, 2-. Those two kind of neutralize each other, and this is a neutral compound, so that means that the oxidation state of carbon in this case must be 0, because we can't add any charges, either positive or negative, without making this a not neutral compound. So in this one, TiOH4, let's look at this one element at a time. We know how to predict O and H. So O is 2-, H is 1+. So 1O plus 1, so 2- plus 1, 1+. That makes this OH part overall -1. And then I have -1 times 4. So I have 4- from the hydroxide part. And since this is a neutral compound overall, that means that the titanium in this case must be 4+ to balance it. All right, and the transition metals, they have variable oxidation states. So you're always going to have to just figure it out based off of context by looking at the compound, or based off of the name, because we know that when we're writing transition metal ionic compounds, that we usually have to notate what the charge of the metal is in the name using Roman numerals. So like copper 2 sulfate is going to be CuSO4 because SO4 has a 2- charge, and in this case the copper is going to be 2+, so they're in a 1-to-1 ratio. Hopefully this is review for y'all though, and you don't need to memorize all the common ions. They'll usually be given to you in context, but it's good to know a lot of them off the top of your head, like knowing nitrate, sulfate, phosphate, hydroxide, ammonium, etc. All right, let's give some practice for applying oxidation states and then knowing how to analyze what's happening in a redox reaction as a result. Being able to figure out which element is being oxidized, which element is being reduced, how to balance that, and then also how to figure out how many electrons overall are being transferred in the equation. So for an example, we have aluminum reacting with hydrogen bromide to make aluminum bromide and hydrogen gas. Diatomic hydrogen. And you'll see that I didn't balance this because one unique thing about doing analysis of redox reactions is it ends up balancing itself in the process. And you'll see what I mean in a sec. So let's first start by determining the oxidation state of all of the elements involved. So aluminum starts as pure metal aluminum, which based off of our rules is going to give us an oxidation state of 0. And then it becomes aluminum in a compound with bromide. And bromide is one of the halogens, which we know always have a -1 in a compound. So I have -1 times 3, which is 3-. And since this is a neutral compound overall, that means that the aluminum must be 3+. So my aluminum is changing from an oxidation state of 0 to an oxidation state of 3+. The hydrogen starts as HBr, so it's going to start as a +1. And since it ends up becoming H2, since it ends up becoming a diatomic hydrogen, it's becoming a pure substance. That means it's going to end as a oxidation state of 0. So we're going from 1+ to 0. And if we look at bromide in each case, we have HBr, so we have bromide in a compound It's going to be -1, and then we end up with bromide still in a compound. So it's also going to be -1. So that tells us that by analyzing the oxidation states of all of the elements here, we can tell that aluminum is going to gain positive charge, hydrogen is going to lose positive charge, and bromine is going to stay the same. So the bromide ions are really not part of the redox here. But we can figure out which element is being oxidized and which element is going to be reduced by the change of their oxidation states. So for example, aluminum is going from 0 to 3+, so it's becoming more positive, and you can only become positive by losing negative. So that implies that the aluminum is losing electrons, which means it's being oxidized. And for the hydrogen, it's going from +1 to 0, so it's losing positive charge, which you can only do by gaining negative charge. That tells us that the hydrogen is going to be gaining electrons, and therefore is the element in this case being reduced. So aluminum is oxidized and hydrogen is reduced. Another way that I like to remember this, besides the oil rig acronym, is that in reduction, the oxidation state is going to be reduced. And so it's going to go from a bigger positive number to either neutral, a lesser positive number, or a negative number. The value is always reducing on a number line. All right, so we're not done here. So a useful thing to do with redox reactions to sort of understand the mechanics and then also balance them and know how many electrons are being transferred is to separate them into what are called half reactions. A half reaction is when I take a redox reaction and I split up the oxidation part and I split up the reduction part into their own individual chemical equations. So to do that, I had aluminum that was neutral becoming aluminum 3+, and this is my oxidation part of it. And I add electrons to the mix because I want to be able to visualize how many electrons are being gained or lost, because that will help us balance the equation and help us determine how many electrons are being transferred overall. So I know it's going from 0 to 3+, which must mean that it's gaining losing 3 electrons per aluminum atom. And the way we write that is by putting those electrons as E- on the product side. Product side means they're being lost, because you can imagine here's aluminum with those 3 electrons, and now here's aluminum separated from them. The 3 electrons broke off of the aluminum, leaving it charged and going off on its own. And now those electrons are free to be gained by the thing that's being reduced, which was hydrogen. So we started with H+ on the product side, since it was HBr. I have effectively removed bromide from this because it's not transferring electrons. So I start with H+, and then it becomes H2. So since it's a pure substance that is diatomic by nature, I don't split it up. So I have H2 on the product side, which means that I need 2 H+ on the reactant side. So even though I didn't have them technically in the original unbalanced equation, I now add it here to make a half reaction that makes sense. So I knew that each hydrogen was going from a +1 to a 0, which means that each hydrogen atom itself is gaining 1 electron, which means that if I have 2 H+ becoming an H2, that's 2 overall electrons being gained to balance this half reaction. So now that I have my 2 half reactions, I have aluminum plus aluminum 3+ plus 3 electrons, so aluminum losing 3 electrons. And then I have hydrogen ions gaining 2 electrons to become a diatomic hydrogen. And since these things are sort of happening simultaneously and in tandem with each other, I need to make sure that both of these agree. Hydrogen can't be gaining 2 electrons if aluminum is losing 3. That doesn't really make sense. That means 1 electron is kind of going off into the abyss somewhere, which we can't have. So I need to make these two agree with each other. And the way I do that is by balancing the electrons. The electrons being lost by the substance being oxidized needs to be equal to the electrons being gained by the thing that's being reduced. So I have a 3-2 situation. So the way we make 3-2 the same is with the common multiple of 6. So I'm going to multiply the whole first half reaction by 2. So I have 2 aluminums making 2 aluminum ions plus 6 total electrons. So 2 individual aluminum atoms that are neutral are going to become 2 aluminum ions, and 6 electrons are going to be lost overall. And then this one, since I need to make it 6, I'm going to multiply this one by 3. So now I have 6 hydrogen ions. Each of them are going to gain 1 electron, so that's 6 total electrons, and we're going to end up with 3 diatomic hydrogens. And that tells us that after we've balanced these two half reactions to have agreeing electrons between them, that in this reaction, in this redox reaction, 6 total electrons are being transferred from aluminum atoms to hydrogen atoms. And then those coefficients that I came up with in the half reactions, I can then reapply back to the original. And then I end up with 2Al plus 6HBr, making 2AlBr3 plus 3H2. That makes sense. Cool. 2Al plus 6HBr, making 2AlBr3 and 3 hydrogen. All right, let's do another example. We're going to now determine the oxidation number for iron and carbon in the following reaction. Because we can see that the oxygen stays as an oxygen ion in both cases, so the oxygen isn't involved here. And we're going to figure out which is going to be oxidized, which is being reduced. We're going to figure out the total number of electrons being transferred, and then we're going to come up with the overall balanced equation as a result. All right, so let's start with this first compound here. I have Fe2O3. So I know that oxygen is going to be 2 minus, so I have 2 minus times 3, so that's 6 minus. And then I'm going to need a 6 plus total on the irons. And there's 2 of them, so that means each one's going to be 3 plus. So iron starts as 3 plus. On the product side, I have iron as neutral. So I have Fe3 plus becoming Fe neutral. And then I have carbon here by itself. So I have carbon as a pure substance. So that means that carbon is going to be neutral. And then carbon combines with oxygen to make carbon monoxide. And oxygen is still 2 minus here, which means that the carbon has to be 2 plus in order for this to be neutral. So Fe3 plus becoming Fe neutral, and then carbon neutral becoming carbon 2 plus. So let's start writing some half reactions for this. So Fe3 plus going to Fe0, that's obviously a reduction because the number is being reduced on a number line. 3 plus is becoming 0, and that's only going to happen through the gain of 3 electrons. So iron is going to gain 3 electrons to become neutral iron. And then carbon, which went from neutral to 2 plus, that must have lost 2 electrons. So I put those on the product side. So I have carbon becoming carbon 2 plus 2 electrons. I have my reduction and I have my oxidation. Now I need to balance the electrons. So similar to the last one, I have a 3-2 situation. So I'm going to multiply this half reaction by 2 and this half reaction by 3. And then what I end up with overall is Fe2O3 plus 3 carbons, making 2 irons and 3 carbon monoxides. You'll notice that I didn't put a coefficient in front of the iron oxide because it already had 2 irons, and which is what I needed from the balanced one. I kind of ignored that in this case because I wanted to look at one iron atom individually. So I have that and then 3 carbons, which I got from this one, making 2 irons and then 3 COs overall. And you'll see that oxygen just happened to be balanced in the process. So if you do this all correctly and make sure that the electrons are being transferred correctly, everything else should fall into place. All right, now let's talk about precipitation reactions. This one's going to be pretty easy to talk about since we already went over double replacement, complete ionic, and net ionic equations. Because these reactions are sort of similar. We're looking at a double replacement. We're looking at 2 ionic compounds that are switching partners and possibly becoming insoluble in the process. So, like I said, precipitation reactions are a type of double replacement reaction where we have 2 soluble ionic substances that are split up into their individual ions, and then we have new combinations of those ions that end up being insoluble, and then they end up forming a crystal that drops out of solution. So we have an example here. We have lead nitrate that's aqueous being mixed with sodium iodide that's aqueous, and then we end up forming a lead iodide solid. Which we can see in this picture is this sort of yellow murky substance that is forming. Very often precipitates will look like a weird liquid that's forming, but if you give it time, it'll settle to the bottom, or if you centrifuge it, it'll settle to the bottom. And that's why we call it precipitation, because it's sort of falling out of solution. Another thing that precipitation refers to is rain, water falling from the sky. So precipitation kind of has to do with falling out. And we can analyze this further by looking at the total ionic and net ionic equations. But the important skill that we're going to be talking about here is sort of predicting the products and determining whether they're soluble or not. And in order to do that, we need solubility rules. So There are a whole bunch of solubility rules that are associated with all kinds of different ions, but there are a few that you need to know off the top of your head. Those are the ones that I have sort of highlighted in purple here. So any compound that contains alkali metals, so like sodium, lithium, potassium, rubidium, cesium, etc., ammonium ions, NH4+, either of these types of cations are always going to be soluble. Any sort of ionic compound that has these cations in it are always going to be soluble. They're always going to be able to dissolve in water and split up into their component ions. Also, any compound containing nitrate is also always soluble. So these three are the three that you have to have memorized. Alkali metals, always soluble. Ammonium, always soluble. Nitrate, always soluble. There's a bunch of other stuff that's always soluble and always insoluble, and stuff that have exceptions to those rules. You do not need to have those memorized. You will always be given the context to figure all that out. The important part is being able to look at a rule set like this and apply it to a chemical equation. So let's do some practice with that. So say we were given this. We need to write out a chemical reaction between ammonium sulfide and barium hydroxide, and then strontium chloride and silver carbonate. Well, first off, let's write our reactants. Let's write down the ionic compounds that correspond with these names. And that's going to look like this. So ammonium sulfide, sulfide has a 2- charge, ammonium is +1, so it's going to be NH42S. Barium hydroxide, BaOH2. I know that these are both aqueous. One, because I know that ammonium is always aqueous. That's one of the rules that you need to have memorized. This one, barium hydroxide, I would look at my rules. Let's see, hydroxide. Here we go. Any compound containing hydroxide anions are insoluble. So most OH compounds are insoluble unless combined with alkali metals, ammonium, or barium. So barium is actually, oddly, one of the exceptions to the OH- being insoluble rule. So that's why we end up with aqueous BaOH2 here. All right, and then for the other one, strontium chloride plus silver carbonate. So strontium is a alkaline earth metal with a halide. Let's see here. What are my halide rules? Any compounds containing halide anions are soluble unless combined with silver, mercury, or lead. We're looking at strontium, which is an alkaline earth metal, so it's not one of the exceptions. So we know that the strontium chloride is going to be aqueous. And then silver carbonate, Ag2CO3. Let's look at the rules there. Carbonates down here in the insoluble section. Any compound containing carbonate, phosphate, chromate, or sulfide, unless combined with, So carbonates are always insoluble unless they're combined with alkali metals or ammonium. In this case, we're looking at silver, which is neither of those things. So we can assume that the silver carbonate is going to be insoluble. So that's why I listed it as a solid here. So next I need to do the double replacement part of this. I need to predict what the products are going to be. So the ammonium is going to go with the hydroxide. The cation of this one is going to go with the anion of the other. And then the barium is going to go with the sulfide. So I'll have BaS and then NH4OH on the product side. For the strontium chloride and silver carbonate, I end up with a sort of a weird thing here because this is aqueous, so it's going to split up in solution. But here I'm starting with an insoluble thing. So what we end up here with is, like I mentioned, we have 2 ammonium hydroxides and barium sulfide. I had to add the 2 there to make sure that it was balanced. But then here we have no reaction because the silver carbonate wasn't soluble in the first place, which meant it didn't split up, and there was no way a double replacement reaction could occur in the first place. So we're not going to have a precipitation reaction here because we're not going to have a reaction at all. So let's look at this first one again. So ammonium hydroxide, I know that even though hydroxides are mostly insoluble, it's combined with ammonium, which is always soluble. So that's going to be aqueous. And then I have barium sulfide. Let's look at my rules. Sulfides are here. They're in the insoluble ionic rules. So any compound containing sulfides are insoluble unless combined with an alkaline metal or ammonium. Barium is an alkaline earth metal, so that does not count as one of the exceptions. So that's why I have BaS solid here. So this is going to be a precipitation reaction for sure, because one of the products that was formed is an insoluble compound that's then going to drop out of solution. Another sort of aside here, if you end up with 2 products that are aqueous, that is also a way to consider that there is no reaction, because if no solid is formed, there's no precipitate being formed. And if we just end up with two aqueous compounds on the product side, those aqueous compounds are going to be split up in the first place. So that means that there was no actual reaction that was occurring. So if you end up writing a sort of a balanced ionic equation where you have a double replacement setup and everything is aqueous, that's always going to be a no actual reaction setup. So that is all I have to say today on types of reactions. Sorry this video was a bit long, but yeah, I'll see you in the next one.